Okay, Physics 11, we're going to continue with some more new material. So we just finished working with momentum, and now what we're going to be looking at is energy. Okay, so work and energy is kind of our next little bit of stuff. So again, you will notice over these next 2 weeks, these last 2 weeks of our online learning, you are going to be getting a video pretty much like every second day. Mainly it's just because I want to cover as much material as I can. You won't be seeing any big major assignments, just little small check-ins, and I just want to be able to cover as much as I can in those 2 weeks to prepare you as best as possible for if you choose to take Physics 12. I will also be giving out a small, like a package of material of reading and practice worksheets and solutions to those who are interested so that they can, continue to work on that a little bit over the summer, just to kind of be as prepared for Physics 12 should that be a course you want to be able to take. Okay, so anyway, we're just going to kind of keep going. So today we're going to be looking at work and energy, and also what happens when work is zero. So it's kind of two little mini lessons combined into one video. All right, so we'll get started. All right, so with this first one, so we're going to be talking about work and energy. So one of the things to talk about is types of energy that we're going to be discussing during this unit. Okay, so we're going to be talking about kinetic energy, which is the energy of motion. We'll be talking about potential energy, which is energy that is stored, and then mechanical energy, which is a combination of both potential and kinetic energy. Okay, so we've already kind of been dealing a lot with kinetic energy when we were talking about like the motion of any objects moving. Those objects have kinetic energy. If you're talking about a rock that's, or a ball that's being held at the top of held at the top of a cliff or something, then that actually has a lot of potential energy, right? It hasn't moved yet, but it has the potential energy, right? So it's stored, and then as you drop it, that potential energy turns into kinetic energy. Okay, in the little momentum lab that you would have done, you would have seen that kind of idea about elastic and inelastic collisions, right? So what happens is that if you set both balls in motion, they would have had kinetic energy, and then when they collided and then reversed, if the collision was exactly elastic, right, 100% elastic, then there was conservation of energy, right? So all the kinetic energy still transferred equally, right? Whereas if it was an inelastic collision, right, what ends up happening is that there's a loss of kinetic energy, right? So energy is lost to the outside surroundings at some point, and you don't actually preserve all of that kinetic energy of the motion of the balls, right? So it kind of affects the collision itself, right? And you kind of would have seen that, okay? But anyway, those are the types of energy we'll be looking at. And when we talk about work, okay, work is basically a transfer of mechanical energy, right? So we just said that mechanical energy was like a combination of kinetic and potential energy, and when we talk about work, it's transferring that mechanical energy from one thing to another. Okay, so a force, right, we've done a lot of work with forces, right, F equals ma. A force does work on an object, and that causes the object to move, right? We've seen a lot of that, where we're like pushing an object across a floor, right? And that causes the object to move, and that force has to overcome the force of friction, and if we are doing work on that object and it results in the object changing in some way, then we know that work has been done, okay? So when we talk about how we calculate the work formula is we take the force, right, that's parallel to the object's displacement, and then we multiply it by the magnitude of the displacement, right, and that will equal work done. So a big key thing here is that the force has to be parallel to the object's displacement, okay? So if we're pushing an object horizontally across the floor, the force has to be horizontal in that same direction, okay? Or if we are trying to push, let's say like push a spring down, right, the top of a spring down, okay, then if the object's displacement is going down, then the force applied needs to be pushing down as well. All right, so that's what we're talking about, where it's the magnitude of the force that's parallel, okay? So when you do that and you multiply force by the displacement, right, force is measured in newtons, displacement is measured in meters, and Newton times meters in this case gives us a value of a joule, right, given by the capital J. Okay, so work units will be Newton meters, which is equal to a joule. All right, so really quick practice problem using this formula. right? So a student is rearranging her room. She decides to move her desk across the room a total distance of 3 meters. She moves the desk at a constant velocity by exerting a horizontal force of 2.00 times 10 squared newtons. Calculate the amount of work the student did on the desk moving it across the room. All right, so fairly straightforward in this one, just really quickly looking at how we would use that formula. Okay, so in this case, right, we said that the formula for work is the force multiplied by the displacement. The question tells us that she's applying a constant force, right, of 2.00 times 10 squared newtons, and she moves the desk a total of 3.00 meters. Okay, so it's essentially like 200 times 3, which would be like 600 joules, right? But again, remembering sig figs, this has 3 sig figs, so we'd either have to put a decimal at the end, showing that both of these zeros are significant, or we could write it as 6.00 times 10 squared joules. Okay, so really straightforward formula to use, right? Take the force that's parallel to its displacement, multiply it by its displacement, and then you're done. Okay, all right, going back. All right, so again, there's the answer. Okay, now notice in that last example, though, it was with constant velocity, right? So remember, we've talked about that before, where if it's constant velocity, then it's, force times mass times acceleration. Force equaling mass times acceleration, the acceleration would have been 0, right? So we wouldn't need to worry about anything else in that sense. However, right, sometimes we're going to have to deal with the overall force in a particular direction, right? So we need to kind of continue to use our net force, right? Don't forget your F equals ma, right? Because we might have to overcome friction, and then our force in a certain direction is going to be a little bit more, right? You're applying the force to move it, plus the force to overcome the friction, and then you're trying to move it a certain distance, okay? So it's going to be more work being done on that. And again, we'll see some examples with that. All right, so let's take a look at this one. So an 83.0 kilogram boy jumps off a cliff and into the water below. If gravity is doing 5.50 times 10 cubed joules of work on the boy, calculate the height of the cliff. Okay, and again, remember that we will need to use 2 different formulas here. F equals ma, and work is equal to force parallel times displacement. All right, so let's solve this one together. All right, so with this one, again, stating the things that we know that the mass of the boy is 83.0 kilograms. Okay, we know that the work being done on the boy, right, so he's jumping off of the cliff, right, falling down, okay, so really it's just the force of gravity pulling down on the boy. There's nothing pulling back, right? We're going to ignore any sort of air resistance in this type of question. But we know that the work being done was the 5.50 times 10 cubed joules, and we are being asked for what is the displacement, right? So if we wanted to, we could say, okay, well, we know the formula for work. Work is equal to the force parallel to motion, right, multiplied by the displacement. We have the work. We're looking for displacement. So to get displacement by itself, we would divide both sides by the force parallel. So work divided by force parallel is equal to delta D, right, the change in displacement, right, which is the height of which he's falling. Thing is that we have work, that's not a problem. We don't have the force parallel. However, the force parallel in this case is just going to equal the force of gravity, because that's the force pulling down, and that's the direction of motion. Okay, so the boy's falling down. That is the direction of displacement. So Fg would be our force parallel in this case. And remember, we can find Fg by taking mass and multiplying it by acceleration, but in this case, the acceleration will be acceleration due to gravity, so 9.81. Right, so our Fg is going to equal our mass of 83 kilograms multiplied by our gravity of 9.81 meters per second. Right, and when we do that, we get a value of 814.23 newtons. Okay, so now we have this value to go here, so our height at which he fell, the displacement, would be that work of 5.50 times 10 cubed joules divided by our force parallel, which in this case is our force of gravity, which is 814.23 newtons. That will be delta D. And when we do that, we get a value of 6.75 meters. All right, so the boy has fallen or jumped from a cliff that is a height of 6.75 meters and 3 sig figs, so we're good. Okay, so we will still be kind of using that same idea, right? Let's look at another problem. All right, so there's your solution kind of listed out, right? Same idea where it's okay. Here's the information that we have, all right? Realize you don't have everything that you need, so you start by finding your force of gravity, all right, and then plugging it in to find work. All right, let's look at this one. Okay, so in this one, a boy on a bicycle drags a wagon full of newspapers at a rate of 0.800 meters per second for 30 minutes using a force of 40 newtons. How much work has the boy done? Okay, so once again, we're being asked for work. Let's start by listing what we have. All right, well, what we have in this question is we have that there's a velocity, a constant velocity of 0.800 meters per second, and it's being pulled at that rate for 30 minutes. And the applied force at which the boy is pulling is 40 newtons. Okay? So he's continuing to apply a force of 40 newtons, which would, and if it's being at a constant rate, it's just overcoming the force of friction to keep it moving constantly. It's not accelerating, and he's doing this for 30 minutes, and we're being asked, well, how much work has been done? Okay, well, we know that the formula for work is that force applied times the displacement. Well, we have the force being applied. We know that that's 40 newtons. That's not a problem. But you'll notice we don't have a change in displacement at this point, right? We know the speed at which it was traveling, for how long, but the displacement's not given to us. However, we can figure that out, right? Go back to our unit on kinematics, right? How can we relate velocity, time, and displacement? And that's just a quick little sidebar, right, where velocity is equal to distance over time. So if we want displacement, it just needs to be velocity times our time. We have the velocity, which is 0.8 meters per second. And our time is 30 minutes. However, we need these units to cancel correctly. So since this is meters per second, we need to convert 30 minutes into seconds. So we just need to take 30 and multiply it by 60 to give us 1800 seconds. Okay? All right, so we just need to multiply this by 60 seconds per minute, and then that equals 1800 seconds. Okay? And now these units would cancel correctly. And 0.8 multiplied by 1800 is going to equal 1,440 meters. Okay, so we know that the boy has actually pulled the wagon almost like 1.4 kilometers at this point, but we need to keep it in meters. So the work done by the boy is that 40 newtons over a course of 1,440 meters. So that gives us a value of 57,600 joules. How many sig figs? 3, 3, 3. So we would rewrite this as 5.76 times 10 to the 1, 2, 3, 4 joules. That's how much work is done by the boy in this scenario. All right, going back. So we have, right, so same answers there, right, showing how we got the distance, the displacement, and then multiplying to get the work done. Okay, so this one would have been an independent practice if we were in class. Feel free to pause the video and give this one a try on your own. If you still don't feel comfortable with it, I'll show you. This one doesn't have the solutions typed out, but I will do them on the board here. Okay, so in this one, we've got a 25 kilogram object is accelerated from rest through a distance of 6 meters in 4 seconds over a level floor. If the force of friction between the object and the floor is 3.8 newtons, what is the work that is done to move the object? So this question really does require you to go back and think about all the work that we've done in dynamics so far about finding net force. Okay, so I would start with the free body diagram here, right? So let's do that. So what you have is this object that's being accelerated from rest, so it has to overcome that static friction, all right, to get it moving, right? And there's an applied force acting in this direction, but we're being told that there's a force of friction acting on it as well. Now, it does say it's being accelerated, which means these would not be equal, right? So we know that in this case, this would overpower force of friction, okay? But we need to figure out, you know, what's happening here, right? So things that we have. We've got our mass at 25 kilograms. We know that it's being accelerated from rest, meaning that its initial velocity would have been 0 meters per second, okay? We don't know the acceleration. We don't know what the VF is actually equal to either, right? So VF is unknown. Acceleration is unknown. However, we do know that it travels a distance of 6 meters over a course of 4 seconds. Okay? And we also know that the force of friction being applied to this object is 3.8 newtons. Okay, and again, we're interested in the work. Right? This is the ultimate thing that we're trying to find. So we can start with that and say, okay, well, if I want to find work, work is equal to the force parallel multiplied by the displacement. In this case, we have the displacement. We have that it's going to move 6 meters, but we don't know what that force applied actually is. Right? We don't know what that net force is happening, well, the applied force happening in this situation. So let's go and take a look at, well, what would have been an equation for net force here? Okay, so our F net, just going to do this over here, right? Our F net, we know, is mass times acceleration. In this case, we have two forces acting on our object, the applied force and the force of friction. The applied force I'll consider as positive because it's acting in the direction of motion, and the force of friction is pulling it back, so I'll subtract it. Okay, now our mass is 25 kilograms, so we know that. And our acceleration right now is still unknown. Okay, so again, we're interested in this applied force. This is the force, right, being pushed, right, that's being applied to move this object. Okay, that's the force we're interested in. So how are we going to find that applied force? Well, again, we can say, well, my applied force would have equaled this 25 times A, and then we would just have added the force of friction to both sides here, and the force of friction is 3.8 newtons. Right, so the question now is, well, what's the acceleration? We know that its VI is 0. We know that it moves 6 meters in 4 seconds, but how does that solve for A? Again, go back to your kinematics formulas, right? Those big three equations, right? So is there an equation that relates VI, D, T, and the A that we're interested in? And there is. It's that lovely D is equal to VIT plus 1/2 AT squared, right? You know that the displacement is 6. You know that VI is 0. You know that T is 4 plus 1/2 times the A that you're trying to find, and then your force squared, right? This is 0, so that's just going to cancel, okay? 1/2 times A times 4 squared, so 4 squared would be 16, times 1/2 is 8, so you'll have 6 is equal to 8A, divide both sides by 8, and you get a value of A of 0.75 meters per second squared. Right? Now that I have A, I can use it up here such that my force applied is now 25 times my 0.75 and then plus the 3.8, right? Because this is a mass times an acceleration, so that'll give us a force in newtons, okay? So that gives us 18.75 newtons plus the 3.8 newtons, right? So this, like 18.75 newtons, would have been kind of the F net scenario here, Okay, but what we're doing is we're trying to find what's the applied force, right? Because that's the force that we need for the work. So we need to then add on the force of friction. So when we add those together, we get that our applied force pushing this object across the floor is a value of 22.55 newtons. Okay, and then that is used in our work formula. So our work done is that applied force, right, pushing in the direction of motion, 22.55 newtons, multiplied by the displacement that it traveled, 6 meters. And when we do that, we get a value of 135.3 joules. Okay? Only thing is, we only get 2 sig figs, right? I mean, this had 3, but this only had 2, and this only had 2, and this only had 2. So how we turn 135.3 into 2 is we round that up to 140. Okay? So that'll be 140 joules, right? Because this is, we only get 2, it'd be 1, and then we get this one. So that would mean this 3, because this is a 5, we would round that up. So we actually would say that it's 140 joules of work being done, right? Because then there's your 2 sig figs. Or you could write it as 1.4 times 10 squared joules as well. Okay? So that's work and energy. Okay? So if we go back there, that's all the stuff for this first part of it. And then there's a worksheet that you can work on at this point just talking about work. Okay? And calculating work or calculating displacement, or, you know, rearranging the formula and being able to find those various things. Okay, now what I also want to quickly add in, and this really doesn't warrant its own lesson, so I'm just going to kind of throw it in here now, is situations where work done is actually 0. Okay, so in this scenario, okay, again, remembering that work is equal to force times displacement. So work would be 0 if either the force being applied is nothing, so therefore, of course, it's not, you know, you could try and move, but if the force applied is nothing, you're not going to do any work, right? Or if your displacement is nothing, okay? Because if displacement is 0, no matter how much force you apply and you multiply it by displacement, your work is going to end up equaling 0, okay? So there are, because of this formula, there are examples exist where work appears to happen, but really nothing's actually been done. Okay, so there's 3 big scenarios that you need to be aware of where it seems as though work's being done, but really it's not. So the first one is, like I mentioned, no displacement occurs. So imagine you're pushing on a house. You might be pushing and pushing and pushing as hard as you can, and you're exerting a lot of force on it, right? You're applying a lot of force, but the house doesn't actually move. So since the formula for work contains a displacement component and the house doesn't move, you have no work being done. You've applied a force, but no work has actually been done on the house, okay? Because it hasn't moved. The second one, remembering that your work formula was the force that's parallel to the motion, right, multiplied by the displacement. So if the force that you're applying is not parallel to the motion of the object, then again, you can't consider work being done on the object. So, for example, if you're carrying a stack of books down the hall, right, you're exerting a vertical force on the books, right, to overcome the force of gravity that would have pulled them down, and then you're walking them down the hall. So the displacement is horizontal, but the force that you're applying is vertical. That's not parallel, that's perpendicular. So there's no work being done on the books with respect to their horizontal motion down the hallway, right? Now, if they were falling, that's a different scenario, right? If you were, or if you were lifting those books, right, then the force applied, right, and then their displacement is vertical, then that's fine. But if, again, it's all about that frame of reference. So if you're talking about this in terms of the books are moving horizontally, but the force you're applying is upwards and it's vertical, then no work has actually been done here, okay? And your third scenario is, again, that the fact that there's no force actually acting on an object, okay? So if you've got something and there's nothing to slow it down, right? So thinking of a frictionless surface. So if you've got a hockey puck sliding along a frictionless ice, even though work might have started its movement, afterwards, no force is required to keep it moving. It's going to just keep going if there's nothing pulling it back. So again, if work is equal to the force parallel multiplied by the displacement, and it just keeps going, moving, with no force being applied to it anymore, then again, no work has been done, right? And again, we're strictly thinking of the scenario of after it's already in motion, right? What's the force required to keep it moving? In this case, none, so no work is done on the object after its initial contact. Okay, and again, that's assuming a frictionless surface. Okay, so again, some other scenarios that we might consider, right? So if we think about this one, so a child ties a ball to the end of a 1 meter string and swings the ball in a circle. If the string exerts a 10 Newton force on the ball, how much work does the string do on the ball during a swing of one complete circle? So again, we would think about this in terms of work is equal to the force parallel multiplied by the displacement, right? And we have a force given to us of 10 newtons, but again, remember, if we're doing one complete circle, and it's talking about displacement, right, the relationship between where it started and where it ends, if we do one complete circle, overall we haven't moved, right? Our displacement from where we started to where we ended is nothing. Okay, so that would mean it doesn't matter what that force is, you're multiplying by a displacement of 0, so the work would be 0. Okay, so again, right, and you label it, this thing, right, one, the motion of the ball is also not parallel to the force being applied, right, and then and the formula for determining work involves parallel force, so the work done would be 0, but also the displacement is 0 as well there, right, so you can think of it in two ways, one with the displacement being nothing, so it doesn't work, but also the string is not parallel to the motion, right? The motion's going in a circle, whereas the force is just in a straight line between your hand, right, and the ball, right? So again, it's not parallel to the motion of the circle. Okay, and again, there's just some textbook questions that kind of get you thinking about whether or not work is being done in these different scenarios. Okay, and then that's that kind of first lesson on work and energy, and we'll continue to look at other different types of energy and work calculations over the next couple of lessons.